Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to introduce Asfandyar Qureshi. He did his bachelor's and master's at MIT, and now he's graduating with a PhD this fall, or this summer. His thesis work is about power demand routing, steering internet traffic to data centers that instantaneously have cheaper power. Mostly that's what I think he'd be talking about. But he's also worked a lot on telemedicine, how you get high-fidelity wireless coverage from ambulances so that doctors can look in at patients as soon as they enter the ambulance. I've known him for a while. We overlapped for almost all my 5 years at MIT. So don't let his soft-spokenness con you into not lobbing hard questions at him. So feel free.
All right, good morning. So what I'm going to be talking about today is sort of a new perspective on request routing policy in distributed systems. And we're coming at it more from the energy consumption angle and understanding how routing impacts that. So let's start with some context. Now, this is probably something Microsoft is acutely aware of. We're building these massive systems with thousands and thousands of servers, and they're growing really rapidly. On the extreme end is Google with an estimated more than 500,000 servers. And these servers are spread out in lots of locations. The main motivation for that is you want to place servers close to clients so you get good latency characteristics. And if you look at one extreme in that, along that axis, you've got Akamai, which has servers placed in hundreds and hundreds of locations. But just because of the size of these systems, they're consuming many, many megawatts of electricity. So you see a lot of important concerns being raised, both by people within the community and just general news concerns about how much money is being spent on the energy consumed by these systems, what the environmental footprints of these systems are. And what I'm going to talk to you about power demand routing, we believe, our thesis is that it can address both of these concerns. It can both reduce expenses. It can reduce expenses by exploiting price volatility in electricity markets. And it can reduce environmental footprints by exploiting the pollution per watt volatility that you see on the electric grid. Yes?
So what's the 40 million number from, and what is it a fraction of the overall budget for operating such systems?
Okay, so the 40 million number so it's based on some back-of-the-envelope calculations, right? And so what we did was we looked at the total number of servers. We looked at their average utilization rates, the data center overhead costs, and so on, right? And we calculated, okay, this is how many megawatts there's a bound in the number of megawatts they're using. And then if you take the average wholesale market cost per megawatt, then you can map that into dollars, right? But in reality, what that is that's just the electricity generation cost, right? So if you look at your electric bills, it's split up into different pieces. One of them is the generation cost, which is, okay, if I'm consuming 5 watts of energy, this is how much it costs to generate that. Then there's all the distribution costs and the utility tax on additional bills and so on. And the details of that vary depending on which state you're in, which utility you're buying from. So when you look at the total bills, they're about 3 times or so of that. That's what we estimate. Now, I'm sure people in this room actually know how much companies like Microsoft and so on spend in these things. I mean, I have some idea about Akamai, but I'm not allowed to say anything. It's, as a fraction of expenses, we'll get into this later, it's growing. It's growing rapidly because things like the relative cost of bandwidth are falling. Right? So it's becoming more and more important. Does that answer? Yeah, okay. So what I was saying was that we're going to talk about power demand routing, which is going to address both these issues. And at the highest level, what power demand routing is you're trying to modulate the spatial distribution of your system's power consumption by updating your routing policy to address that. Now, what does that actually mean? Well, we have to start with the individual server to sort of understand where we're going, right? So if you look at a server, the basic thing it does is it gets some, so this is in web services like search and so on, right? It gets some requests, client requests, it does some processing, and it produces some responses. Now, in doing that, it consumes some energy. Now, it turns out that as you increase the load on that server, the amount of energy increases. So the marginal increase in energy relative to the request you're adding to it, it's positive. So the more requests you add, the more energy gets consumed by servers. Now, people who've studied this stuff, as first-order approximation, if you look at just the average server CPU utilization across lots of servers for things like web search, you can sort of say that the power consumption of that cluster is linear. Now, it's a lot more complicated than that. And in the paper, we go into some detail in trying to look at published reports and trying to come up with a reasonable power model in the SIGCOMM paper. But this is still an open... it's a complicated question. How proportional is the amount of power consumed by clusters to the amount of load you place on it? So at the base level, there are things like what the hardware details of your servers are, right? Depends on low-level hardware power management issues. Then there's more stuff on on-demand server scaling. Are you turning off idle servers in your data centers? If you do that, then clearly your power consumption is going to become more and more proportional. Now, if you just look at the hardware power management side of the picture, right? Just the stuff that's already deployed in servers. If you look at off-the-shelf servers, the sort that Akamai and so on buy, and you turn off their power management, at idle they're consuming about 95% of their peak power. If you turn on their dynamic voltage scaling and so on, that drops down to about 70%. And if you look at mobile processors, which we've gone and measured, things that we're running, say on this laptop, processors that are now newly designed to be proportional, on idle, they're consuming 1/3 of their peak power. So proportionality is increasing. And people who've studied this in the data center, in data centers, so for instance, there's a Google study that's published. They measured power consumed by multiple racks in their data centers. And what they found was that if you just looked at the CPU utilization, you could predict the amount of power to reasonable accuracy just by using a log linear power model that went from utilization to watts consumed. And this is all without factoring in on-demand server scaling, right? So
what application did they look at?
they looked at web search. Well, actually, they looked at one of their data centers. I don't think in the paper they say exactly what applications were running on it. I think they're a mixture of whatever they're running on it.
Define exactly log linear.
Log linear. So it's the equations later on in this talk, but they'll go from power is equal to 2u, some function of 2u minus u to the power of 1.4, right? So I mean, linear works reasonably well. If you want to be a little more accurate, that works better. Okay, so the whole point of this is to say that there is a significant amount of proportionality that exists in today's servers. And if you look at the hardware trends and the data center trends, proportionality, you're going to see more and more proportionality.
And those servers, what kind of servers were they? Were they power management type servers, or which of those types?
No, those are custom servers.
So it was log linear, but it was in this 5% band.
Well, so but that was measuring things in addition to servers. That was measuring routers and
So
the rack stuff. Yeah.
Well, okay. So our network components, how does their power react?
Routers are a lot less proportional. So we looked at some measurements of, say, core routers, and they're closer to this 95% thing, and they don't actually have stuff built into them that you can turn on that would make them more proportional. I suspect the reason for that is people are so concerned with making sure that latencies are great and everything, they don't bother.
They're only 4% of the total power problem. Not worth it.
Sorry, just following up on this question here. When you say the power is a log linear function of utilization, you're talking about the power consumption of the entire rack, right? Or the entire data center, or what?
No, I think what they measured was things like they measured it on the PDU level, and the way their stuff was set up, the PDU was feeding multiple racks. Right. So this is collections. Yeah, right. So this is, if you measure individual servers, you get weirder power models. But if you have enough of them, it turns out that things are linear or log linear. Yeah. But okay, so what power demand routing does is it tries to take advantage of this proportionality. And the fact that we project increasing proportionality means that it's going to become easier to do this. So what is power demand routing? So let's focus on so-called internet scale systems, right? Think of web search and CDNs. And what we're thinking about are lots of servers divided up and spread out into multiple clusters, which are geographically distributed. And the services are replicated across them, and you've got some clients coming in, and there are flexible request routing layers that can route clients to the servers. Now, the flexibility comes in because you want, if there's a failure, you want to be able to reroute clients to other locations where they can be served by live replicas and so on. So this stuff is already deployed. But if you look at the power side of the equation, right? So let's say your request routing policy divides up clients in this way, right? So you're going to send those 3 to Virginia, those 4 to Illinois, those 3 to California, right? Now that's going to set up some power consumption, geographically distributed power consumption of your system. Now if you update your routing policy and you take some of your clients from Illinois and you send them to Virginia, you're going to increase the power consumption in Virginia, reduce it in Illinois, and similarly if you do that for California, you're moving some of that power demand to California. Now, there are 2 things to note. First, Illinois is still consuming a reasonable amount of power, right? So you can't move everything around. The other thing is we're not actually saving energy. In most of this talk, you can use this technique in ways to save energy, but throughout this talk, we're not really going to talk about that aspect of it. What we're just going to talk about is shifting energy around, right? So the same amount of energy from one geographic location to another location. The cool thing is you're doing this at internet speeds. So, this stuff is you can do within in less than an hour. You can update your routing policy. But why would you do it? Well, as we alluded to before, you do it because you want to reduce costs. So you might be shifting this power to where it's cheaper, or you might be you want to make your system greener. So you might be shifting it to regions with greener electricity. Now, there are 2 critical factors that determine how much energy you can shift around, right? One of them is you need sufficient excess capacity, right? So you can't do this when your system's running at peak load. You can do this, essentially what you're doing is you're shifting idleness around geographically, right? So if you have enough excess capacity at some point in time, you can shift your load around. The other thing you need is this power proportionality, because if you didn't have power proportionality, it wouldn't matter how you were routing requests around, right? So once you have these 2 factors, you can start addressing cost and greenness. And so the rest of this talk is structured so that first I'm going to talk about how to apply this technique to reducing electricity costs, and then I'm going to talk about how to apply this technique to make systems greener. Yeah.
How about latency? Users would see different latencies depending on where they're going.
Yes, that's true. Usually the dominant goal that these systems, the routing policy is trying to do is it's trying to minimize client latency, right? Now, there is some trade-off between latency and reduced costs, and we explore that in our analysis, right? So,
would Illinois have a minimum commitment over some period of time? If they're pulling 10 megawatts from the fan or whatever they're getting at, would they have some commitment?
Right. So yeah, the picture isn't always that simple, right? It's not always, you can't just route electricity around. If you've got a big data center, maybe you've bought a contract or you've committed some amount of energy. One way to think about that is that, say energy demand goes, there's a heat wave in Illinois, everybody turns on their ACs. I don't know if this happens in Illinois, but suppose that happens, right? People turn on ACs, there's consumer demand that increases, right? Now, even if your data center is committed to a certain amount of consumption, it's in everybody's interest if you move it someplace else and you resell that electricity or you free it up into the system, right? So you can think of it that way, that the computation in these systems is fundamentally different from all other sorts of work, right? You can't pick up a factory and move it in an hour 500 miles away, right? In this way, you can route megawatts of electricity around, right? And so you can interact with the grid and improve the social good. It's hard to quantify that, so what we quantify on is reducing the bottom line for companies running these systems. Yes?
This is assuming that the costs are sufficiently dynamic, right? Because otherwise, suppose it makes sense to move people out of the Illinois data center, then you should always move people out of Illinois data center, shut it down. Just add a little bit of extra capacity to California and Virginia, and never, that's it, you shut down your data center. Why not just do that?
Well, so the way we're looking at it is as an economic optimization, right? If you're earning something from the clients you're serving, right? And if the amount of money you're spending by having a presence in Virginia is increasing what you're earning, right? If that difference is large enough, then you should have servers there, right?
Right.
So because of the way electricity prices and so on fluctuate, maybe you want to move away when they get too high.
I see. So
Right.
the
other...
there's another assumption here, right? The critical factor is that electricity prices need to fluctuate at a sufficiently low time granularity. If they don't, if they were constant or if they were built like bandwidth, then you would just shut down the data center in Illinois, right?
Well, there's some service cost function at each location, right? Whether it's electricity price based or carbon cost based or whatever you want to say. Each location has some time varying cost function, right? And as long as those are locationally differentiated and reasonably uncorrelated, then you win by shifting things around, right? If they're correlated, even if they vary, then you don't win anything, right? Right.
Okay, I'm just going to ask this label, I'll ask you now. Are you also, in your model, going to charge yourself for effectively the depreciation cost of the unused servers? So you need to have excess capacity, but that excess capacity is incurring costs whether used or not. Does that end up
No, not...
helping out some of the potential benefits?
So the analysis we did hasn't looked in detail at what the optimal server distribution strategy is, right? What we did was we looked at existing server distributions, and we're assuming that people are already doing optimizations for all these other factors and building costs and energy, average energy costs and bandwidth costs and client latencies. And once they've done that, these techniques can then further reduce your total operating expenses. Right?
Your assumption is that they've already done the regressions to find the right amount of excess capacity to have.
Right.
And that's the question of where should you let the idle stuff?
I mean, that's a very hard question, right? And it depends on so many factors. If you're Akamai, your functions for determining that are very different from if you're Google or Microsoft, right?
There's no place you said CDNs. Is it really? Well, so you put CDNs up on your list of possible applications, and you just said Akamai, so now you've said it twice. Do you seriously think that it makes sense to ship CDNs all the way across the country? I thought the point of them was to put copies close by so that you don't overload the core of the internet. So moving content distribution transcontinentally seems counterproductive.
Well, so it turns out that the actual distance you're moving it isn't important because the grid isn't perfectly connected, right? If you move it 100 miles to your west, which is not that much in terms of network latency often, you might end up in a different part of consuming energy in a different part of the grid that increases the overall efficiency of the system or has a big cost reduction if you're at a market boundary.
I think Bill's point is really good. You put the CDN there because you can dump that traffic onto, let's say, a given tier 2 ISP for almost nothing. If you move it to the other side of the country, you can't.
You have to put CDNs are location sensitive. So web search isn't good.
Let's come back to that when I talk about when we looked at the impact of latency constraints, right? Because we did look at, say, how much latency is Akamai on average willing to accept, and constraining ourselves to that.
Right. So I think fundamentally, I don't know, this is not how the power grid works, right? It's not about saving energy. It's about demand and supply. If Illinois generate that amount of energy and you tell them that I have a data center here, I'm going to consume 100 milliwatts in power, and you only consume 50 milliwatts, then that's a waste. And the power grid would never like somebody to behave like that, right? It's all about smooth.
Well, it used to be. Now it's more about interactivity. So the power grid would love to be able to tell you, okay, I need that extra 10 mega, or I need some number of megawatts because people are consuming more than I thought they would be, or they've plugged in their electric cars and they're drawing more energy than I projected, or my wind power isn't generating as much as I thought it was, or it hasn't rained in a while, and could you please move some of this electricity somewhere else, right? So
that I can understand, but the goal of saving energy is different from being flexible, right? And elastic about the energy.
Right. So yeah, this whole talk is going to focus on. None of it is going to reduce the watts, the total watts of the system, right? It's going to.
Money, not power. Yeah.
Right, or energy, right? The same number of joules. It's just, you just move something. Right. But if you look at power contracts, you'll find a couple of things. One is there's a class of power contracts that typically go to aluminum smelters that say, because they're huge demand, and they say, we'll sell you power cheaper if you agree to turn off when we tell you that we have load. And aluminum smelters don't have the same kind of latency constraints as data centers. So, right, if they add a couple days latency to save 30% in their major input cost, then that's fine. But the fact that the power companies are willing to do that says that they really care about peaking load. And the other thing is, if you look at data center power contracts, what you'll find is that the power cost is nonlinear in the number of watts, right? The cost per joule is nonlinear in the number of watts, which is to say, you get a contract that says that you have a base load power of X megawatts, and then your cost per joule per kilowatt hour is a certain amount of money, and then when you go above that, the cost is typically substantially higher, factor of many higher. So the cost curve for power is strongly nonlinear for data centers.
So I guess we assumed it was linear. We assumed it was indexed to wholesale market prices. But the stuff you brought up about the aluminum smelters, that's a lot more general now. It's something called demand response. So you have companies that are essentially, what they're doing is they'll go to 10 hotels and they'll say, let's package you together and sell you to the grid as somebody who is willing to reduce load. And what the hotels do is they turn off their laundry machines when the grid tells them to. And so that sort of stuff is happening on a much more local level than just factories and so on now. And so the EPA actually studied whether or not data centers could take part in these demand response programs. And the idea was that no, they really can't, because you can't turn off a data center, right? If the grid, or you can't reduce load. In an individual data center, you don't want to give up control to the grid, right? But in these distributed systems, you're not really, what the control you're giving up is rerouting stuff around. So it's a spectrum of performance rather than a hard drop where you have to turn your data center off, right? Okay, so moving on. So what I'm going to talk about is how to use this technique to try to reduce electric bills. And a lot of this material is some of you have seen this before in SIGCOMM and in hotnets. So some of this stuff came up in the discussion, but there's a lot of concern about increasing electricity expenses in these systems, right? What you're finding is that companies like Microsoft and so on, if not already, they're spending millions and millions of dollars on electricity every year. The numbers I have up here are for Google, don't hate me for that. But we know they're spending on the order of $40 million a year just in generation costs, as I explained. When you look at Akamai, the indirect expense of the energy they're consuming is on the order of $10 million. Now, they're not actually paying directly for it because of the way their contracts are set up. But that's a lot of money flowing into the electricity that's being consumed by these systems.
Do you know what the total operational cost of Google is?
No.
It could be 1% of their overall cost.
Well,
Honestly, those numbers seem low to me.
They do to me as well, but they're conservative. Wherever I could make a conservative estimate, I did to get them, because for instance, MIT as a campus pays $62 million a year on their electricity.
There's no way that Google only spends $40 million a year on electricity. There's no way, right? I mean, that would be it. If that were true, then none of this would be worth bothering with for Google, because that's not a noticeable amount of money for PowerPoint. No, really, $40 million, right? They're a multi-billion-dollar corporation, so we're talking a 1 or 2% effect.
Given the latency it hit too.
Yeah, the numbers, but what I'm arguing is that he's over-conservative. I mean, the effect is bigger than this.
Factor of 2? 10.
I bet my head it's 10. I mean, I'm doing this without having done the math that you did, but that number seems way too low.
Well, I'd love to, if I can boost those numbers up, my savings go up, right? So I'm happy.
I think it's 40
It has 1 0.
I think it's a little bit, Bill, a little unfair.
I made up the 10.
Yeah, so I think you should go on. I don't think this is, like, whether you're saying 40 million, 10 million, 5 million, I think it's
Right, so you're right. It doesn't-
I like to think of these things in terms of fractional reductions, but all my other collaborators like to think of that, putting them in dollar terms. So that's why most of this stuff is going to be in dollars.
We did it for Microsoft. We came to 15% of cost.
Okay.
All of it.
Of which?
The cost of the servers, the hardware cost, the capital cost, the generators,
Data center
the
cost.
building,
Monthly,
all the whole
amortized
The number of servers for Google is 500K only in the US or worldwide?
So that's an estimate that's a couple of years old now, but this was for global.
Worldwide or US?
Yeah, this was global. They're probably larger than that. But the thing with Google is they're building these stripped down servers anyway, so their per server wattage is a lot lower than, say, Akamai. It's about a third of what Akamai's is.
Should give you some chance to accelerate.
Okay. So, well, the cost, clearly everybody agrees there's a lot of money being spent on electricity. And they're growing because part of the reason is that these systems, you're adding lots and lots of servers to them over time. And whatever energy efficiency gains that the hardware is making, you're outpacing them. And the relative cost of electricity is increasing. So bandwidth costs are going down if your services aren't using a lot more. So if you're search or something, you're not using an order of magnitude more. The amount of bandwidth you're using isn't increasing. You're going to be spending less and less on bandwidth and more on energy in relative terms. Right. So what we want to do is we want to try to control these. And there's two general approaches to attack this. One is just let's go and reduce the amount of energy consumed. Right. There are other side benefits of that. It makes these systems more manageable. It makes them greener. The other thing you can do, of course, is to reduce the cost per unit energy. And people go and build their data centers in all sorts of remote places where they can get cheap energy. And what they're doing is they're doing a static optimization based on, in part, on electricity costs to do that. What we're proposing is to use that power demand routing approach to try to exploit electricity market dynamics. So when you look at electricity markets, prices fluctuate on an hourly basis, and they fluctuate in an uncorrelated way across different locations, and we're going to try to route based on that. So we're going to couple live data from markets with the routing policy, and hopefully everything will work out and we'll see a reduction in overall expenses. And the idea is you're trying to skew load across your clusters, but you're trying to skew it based on your real-time prices. Now, when you're talking about skewing load, there's another variation on this that we're not really going to talk about. So you can actually improve the energy efficiency of your system if you look at the dynamic energy efficiency of your clusters. So if someplace is very warm and you're having to turn on, you can't run passive cooling there and you have to turn on your HVACs, and another place is colder and you can use passive cooling or something, if you skew load based on those issues, you can actually reduce the total amount of energy consumed by your system. So you can follow local weather patterns, you can follow things like, if you're doing on-demand server scaling, then the energy efficiency of your clusters might change based on which servers are currently activated, and so on. But what we're going to focus on is just let's keep the total energy constant and let's try to reduce the cost of it.
The cooling system doesn't like this variation of load either. If you change the heat generated in the data center at a minute level fluctuation, the AC system will just react really.
So let me just say just a note about timescales. When we're talking about adapting, we're talking about adapting once every hour throughout this talk, roughly, right? So that at that level, we're assuming that the routing updates can propagate through the system. We're assuming that if you have advanced warning, these issues with cooling and so on work out. But yeah, so we're not talking about doing very fine-grained adaptation. Yeah.
So feel free to point if you address this. I came in a little late. So do you take into account communication with the local utility itself? Because if underneath you're changing the load, part of the way the utilities bid for energy is based on historical data about usage. Now you have this data center, which could be a significant fraction of the other utility serving you, and you bring in this lower layer adaptivity, suddenly it goes up. So are you accounting for that, or are you assuming that utility can supply you infinite amount of energy?
No, so, okay, so the way prices are set, right? So let me just actually call up this next picture. So when I say price volatility, right, clearly not a lot of people in this room know about wholesale electricity markets and what's happening on them and so on, because this hasn't become common knowledge yet. But these are prices from what's called the real-time wholesale electricity market for 3 different locations, right? Illinois, California, and Virginia. And you can see a lot of variation across that, right? So there's hour-to-hour variation in the dollar cost per megawatt that you buy from the grid on this market. Now, the way these prices are set is, so this is the real-time market. There's also a day-ahead market, which is sort of futures market. What happens is every day, everybody who wants to consume electricity on the grid goes and they present a bid that this is how much I'm willing to pay for this much energy, right? And all the producers, they present these bid curves. And there's an auction, and that sets hourly prices for the next day. And then, so that's all based on projected load, right?
Who are the players in the market?
So utility companies, power plants.
We write long-term contracts.
Right.
Are we a player in this market too?
You can be. I don't think data centers are right now. So the wholesale markets account for about 40% of all energy traded in the US, right? Everything else is done on these long-term contract bids. Now, the economists who've studied this stuff, what they tend to argue is that if you have flexibility in your consumption, that it's better for you to be on these wholesale markets than it is for you to be hedging your bets with long-term contracts. Now, even if you have a long-term contract and you're buying electricity, you can always resell it on this market, right? So the day-ahead market I was talking about is based on projected load, right? And that sets for the next day, it sets prices for every hour. What this is the real-time market, which is whatever is left over is traded in some sense, right? And the reason we focus on the real-time market is because there's a lot more variation in prices in the real-time market because your supply is more constrained. And it's not infinite, but the amount of energy being traded is more than data centers are using, right? So we haven't looked at locational issues that maybe you're in a location where your grid constraints start becoming a problem, right? You don't have enough transmission lines to buy a lot of energy quickly. But if you just look at the amount of electricity being traded on these things, it seems reasonable for single data centers, not maybe the mega ones, but the smaller ones to participate in this. Yes.
Are the prices on this real-time market around the same as say, the day advance market? Or are they extremely higher?
No, I mean, we've got some numbers on that in the sitcom paper, but they're close. They're not. They're in the same ballpark, but there's more variation.
Are the times of the day the same? Because California is in the Pacific area, Virginia is in the east, Virginia is in the center, and there are these peaks that suggest certain patterns of use of the energy. California suggests that the energy is more expensive in the morning, maybe.
So the time axis is UTC, right? So these are all corrected. So I mean they're only 3 hours apart, so you don't see. We tried to we tried to do these. Initially, it seemed like a great idea. Let's exploit the time difference where there should be big savings there, but it turns out that there's not. All these other factors, these auctioning factors, tend to dominate.
Do you also look at the circadian rhythms?
The what?
Circadian rhythms.
A little bit. It turns out that if you're trying to predict prices, the hour of day is a reasonably good predictor.
Meaning around the year.
Oh, for the prices. Economists have studied that. Traders have studied that because they'd love to be able to trade this stuff and trade derivatives based on this stuff.
Have you seen that? Have you seen that pattern?
No. I mean, there might be some weak ones, but yeah.
Okay. You need to go forward. Just a quick clarification. RT market prices, are we talking the spot prices here, or are these?
Yeah, spot. These are the spot prices.
So so this is energy now.
Yeah, so this is the spot market as opposed to the future market. Yeah. So if you buy electricity, you're not going to be paying exactly this many dollars, but there's a lot of places which offer prices that are indexed to this. So there's some function of these prices, right? Some linear function or some. But anyway, so there's a lot of variation. It's uncorrelated. And these aren't just 3 random locations. These are the large data center markets. The maximums are very large compared to the median prices. And you see things like negative prices So at some points, you're going to get paid by the grid to start consuming electricity at that location. And that has to do with congestion on the grid and so on. So if you consume electricity at a certain point in time, you're increasing the overall efficiency of the grid. But the thing to keep in mind is the uncorrelated locational pricing. Now, if you just look at two of these signals, the intuition for what we're trying to do is we're trying to stick to the lower envelope in terms of dynamic price, right? We're always trying to pay the minimum price at any given point in time and shift load around so that we do that. Now, we start out with, and we're going to do this by playing with routing policy. So we start out with this schematic view of the routing policy in the system, right? So we think that there's some requests coming in, there's some performance-aware routing scheme that's generating a traffic matrix that's splitting up incoming traffic to your clusters, and it's taking latency goals and capacity constraints and knowledge about the network topology and your bandwidth constraints and so on. And what we're arguing for is to replace it with a slightly modified module in the center that additionally factors in real-time market prices and updates the traffic matrix, whatever optimization problem it's doing internally. Right. So it's not entirely clear that this idea of routing around based on prices will reduce total costs. We've already said that you have to have sufficient proportionality and sufficient excess capacity for this to even consider doing this. But we're not only concerned with moving power around, we're concerned with moving power around to reduce costs. So you have to look at the other cost components of the system. So there's bandwidth costs. It could be that wherever there's cheaper electricity, it tends to be correlated by some fluke with more expensive bandwidth. It could be that your latency concerns are so stringent that you actually can't move power around with the flexibility you need to exploit the economic value there. So how far away from clients is this cheap energy? And so we looked at all these issues and we tried to model a system and try to quantify how much that system would have saved if it had gone from a price agnostic routing scheme to a scheme that actually factored in electricity prices. And so these, we already alluded to these a little while ago, but if we looked at a system model that was based on Akamai and power information from Google and bandwidth prices from Akamai and so on, we're seeing that with today's level of power proportionality in servers, you're getting to the point where $1 million a year is reasonable. So this is about a 5% reduction in electricity expenses. And as the proportionality increases, we project that the savings from this exploiting volatility go up by an order of magnitude because your proportionality just seems to be rising so quickly. Yes.
This is assuming the bandwidth cost and the latency costs don't change?
This is accounting for them.
But this is accounting
for bandwidth and latency.
So how do you account for latency?
We'll get into both. Not latency cost, but we just put a hard constraint on it. But the last point I want to make is that we found that if you don't pay that much attention, if you cut out the bandwidth and latency part of the equation, you can the dynamic solution, dynamically optimizing your electricity prices is better than trying to statically optimize them, right? So if you took all your servers and put them in the place that gave you the lowest electricity costs over the whole year, right? That's worse than spreading them out and dynamically shifting load around.
So $1 million a year doesn't pay the salaries of the people who write the system.
That's true.
So
cut me off if you are going to talk about it. What are the insights? What about the system lets you get away with latency constraints and save money? Or what could you do to improve the savings?
Well, so the single, we'll get into. I'll get into exactly what impacts the savings, but I think I'm going to get into all those things in a second. Okay, so we spent a lot of time trying to quantify this just to make sure that we're getting at least some percentage reduction in the cost. If it's not just noise, that we're seeing 0.1% reduction or something, and it looks like we're doing well. But the way we ran this analysis was we went back to that routing schematic and we set up this analytical framework where we start with a workload, we start with a lot of data on electricity prices, and then we step through that workload and those prices. So for every hour, we do a routing optimization and derive a traffic matrix, and then take that traffic matrix and use a power model to generate an electricity cost for the system, right? And by doing this, then we can look at different workloads and different electricity prices and different routing schemes and figure out how much we would have spent on electricity if we had used those routing schemes.
You use proprietary data from Akamai to do this.
Yes, for the network topology and the workload, yes.
And the costs.
The electricity costs?
Bandwidth costs.
We'll get into how we dealt with bandwidth costs. They weren't actually willing to give us bandwidth cost numbers. So one of our collaborators went and talked to their people, and so I got secondhand info. And there's stuff in there that I'll just get to how we dealt with the rest of the issues. But it would have been nice to know about bandwidth cost data. Right, so the whole point was to get to these electricity cost numbers and then to compare the impacts of different routing policies. Now, actually, this addresses your issue, right? Which is, there's a question about the generality of the results because a lot of our analysis is based on very Akamai-specific data. So things like where their servers were distributed, how many servers were in how many locations, the workload itself, and capacity and bandwidth constraints. These all came from Akamai. Now, we think that, first, we're trying to put ballpark figures on savings and see if this actually, this approach is promising. So the results that we have, not the numbers themselves, but the general trends, should be applicable to other systems. First of all, the workload itself is very broad. So they're serving 2,000 content providers, right? So we're getting a large slice of the web traffic. And they're handling hundreds of billions of requests per day. So it's not like we're getting a very small sample of the web. And the server distribution that we used, it's a realistic server distribution. We could have come up with synthetic ones. We actually did analyze synthetic ones, but the numbers that we have are for something that's real, which is better than speculating. Okay, so I'm going to step through each of these aspects of the analysis. And so let's start with the routing scheme that we used. And we tried to come up with the simplest sum routing scheme we could explain in one paragraph as a delta to existing routing schemes. And so what we say is that, after you've done your performance optimization, you've got some candidate, you've got a client, you've got some candidate set of clusters, just pick the one with the lowest price and account for things like capacity constraints. And the assumptions that go into this are that, there's complete replication in our analysis. We've looked at partial replication more recently, and we've got some ideas of how to deal with that. But another assumption is that you've got hourly route updates are fine. You're not going to destabilize the routing in the system. And initially, we go in by assuming that bandwidth pricing is uniform, locationally uniform. So wherever you are per bit of bandwidth, you're paying the same. And we'll relax this later. So the next thing is to get a workload that drives our analysis. And so what we did was we went on Akamai CDN and we just measured traffic for 24 days. So we measured how many hits they got, where those hits went, where those hits came from. And so now we had 24 days of exact traffic matrices. And then we derived a synthetic matrix from that, a synthetic workload from that, so that we could actually evaluate longer periods of time than that itself. Then the final thing we needed was electricity prices. And so we went and we collected a lot of data, and this was kind of painful, but we went to a lot of public sources, some private sources, and we collected historical price data for electricity markets. And so we have about 40 months worth of market price data at about 30 locations. Yeah.
Sorry, can you go back to the previous graph first?
It's Chris. That's why it looks funny.
No, well, I was actually wondering where these 25 cities are, because there is clearly a diagonal pattern, and if these cities were spread worldwide, then obviously you won't see that, right? Would expect some sort of smoothing up.
So this is aggregate requests per second. This is global traffic, I think.
Why do you see this diagonal pattern?
Why is what?
Ocean is very large.
The US portion is very large?
Yeah.
The Pacific Ocean is very large.
No.
Oh, yeah, the dips themselves?
Yeah.
Yeah, the dips are the Pacific Ocean.
Yeah, that double dip thing that you see is the normal, the normal, and the bottom is, but it's in the Pacific. Right. So you get U.S. and Europe.
Yeah, we could spend a lot of time talking about this one graph, but generally speaking, the dips are the Pacific Ocean. There's a flatness when you get to the top because there's so many different time zones of getting aggregated, but the U.S. is still dominant, so you still get a bit of a peak there, right?
And the plenty multi-day dip is Christmas.
Yes.
So
Yes, that is Christmas.
And New Year.
Yes, Christmas and New Year. So.
Yeah, there's everyone going home at midnight on the first. Sorry. Keep going.
Okay, all right. So less interesting to this audience is all the electricity price data. There's a lot of graphs in the paper. It's too many to. We did a lot of analysis of trying to understand how prices were varying and how we could exploit that. One of the main insights from that was that if you look at two locations and you look at what's called the price differential, which is prices at one minus the prices at the other, if they're distributed along, if they've got a zero mean and they've got a high variance, right? This means that if you want to pin your location to one of them, you can pin it to either one of them, right? Because their mean prices are the same. But if you start shifting load, then you can capture all the value represented by that variance. So our approach works. And we found there were a lot of pairs in these 30 locations that had those sort of price differentials. And so we proceeded expecting to see some savings. Now, so we have a workload, we've got a network topology and so on, and we need a power model to map traffic to watts so that we can then map watts to dollars. And so we picked this power model, which was based on that Google study I talked about. And the idea was that the power in watts of a cluster is some function of the number of servers at that location, the average CPU or the average cluster utilization, the ratio of the idle server power to the peak server power, and the data center PUE. Right. So what you get, in essence, if you assume that you get are these different curves for different locations, right? And the curves are different because different locations have different numbers of servers. So you get locational differentiation based on that. Now what the graph shows is relationships that are linear in server utilization, right? So that's a reasonably good first approximation, but we used a slightly different function that sort of simplifies to that, which is a more accurate representation of how much power it's using based on its utilization. So we have this model. Now we can. It turns out, So it turns out that there's a lot of details in the model, but in order to look at what our technique is sensitive to, it turns out there are two important parameters our technique is sensitive to, and these are both power proportionality parameters, right? So the ratio between a server's idle power and its peak power, the lower that ratio is, so the lower you can drive idle power, the better it is for our technique, right? That's fairly straightforward. The other thing is, the better data center PUE is, the lower power overheads you have in running your data center, the better our technique is, because then, again, the overall system is more power proportional, right? And together, these help determine how effective the power demand routing is going to end up being. And to see that, let's start talking about results. And so we're going to look at the results being how many savings our technique projected. And we're going to look at them in terms of, let's vary the proportionality in the model, let's look at accounting for bandwidth prices, let's look at accounting for latency concerns, let's look at accounting for market diversity issues, and see how the savings change along all those axes. Right? So let's start with this. Now I said that there are two parameters in the model that are important, right? So these are the two parameters. Now don't pay too much attention to the numbers there for a second. Just on the x-axis, what you see is as you go towards the right, there's increasing proportionality. What is on the y-axis is the percentage reduction in electricity expenses. So how do we calculate that? So for each power model, right? So for each selection of power model parameters, what we went and did was we simulated that request routing scheme. Then we calculated the cost. Then we looked at Akamai's request routing scheme and calculated the cost from that, which we assume is a price agnostic because they're not factoring in electricity prices. And then we looked at the difference, and that's the savings. And so for this is done for that Christmas period, that 24-day period. So the numbers here are, if they had in those 24 days done what we say they should have done, then this is a number for what they would have saved. We've also got this for 3-year periods, and you see the same basic trends. But what you see is that savings accelerate as you increase proportionality, right? So, but let's try to parse out what the x-axis means. So at this point, this is the PUE and the idle to peak ratio, this is what you get with off-the-rack servers, and 2.0 is in the average PUE across data centers in the US. This is where Google was in 2008. So we know that they were very aggressive about minimizing their PUE, and they've got these custom servers, and if they're doing that, then their savings would have been double what you would get with off-the-rack servers, right? Because there's a lot more power proportionality. This is a bar with the EPA's targets for 2011 PUE. And if you used active server scaling, so this would be a reasonable model for that. And at this point, you're closing in on a 10% reduction in your electricity expenses, right? So at this point, already, the technique is becoming fairly, it's paying off. Now, the thing to note is that as you're moving in this direction, there's that rise in savings, but we are moving in this direction. Everything from the way people are building servers to the sort of research that's being done in allocating servers on demand and being more proportional just to reduce total energy expenditures is moving us in that direction. So the technique itself is becoming more and more relevant as technology advances along the vectors, it seems to be. Yeah.
So when you say, this is also true for smart grid technologies, what you're basically doing here is playing an arbitrage game. And the thing about arbitrage games is when one small player is playing, the model works perfectly well. When that player gets really larger, lots of people start playing. That means prices are actually going to adjust based on the fact that there's all these people playing the arbitrage game. And so that would argue, in fact, that in the opposite direction, the more people who do this, the less money you're going to save, because the more the markets will automatically be compensating for these fluctuations.
Right, that's a valid point. One assumption throughout all this is that our actions don't affect the market, right? That assumption is valid if we're small enough players. If you assume that, okay, so the reason I think that that's going to be a valid assumption is because data centers are still, there's a lot of energy going to data centers, but compared to a city, it's nothing.
But you're not the only one playing this game, right? When we talk about plug-in hybrids and charging at night in the smart grid, those are all contributing to this. Right, but those are all playing the same arbitrage game.
Right, but it doesn't really help us to move stuff around at night because there isn't a lot of load. So at night, prices are depressed everywhere. What we're actually winning from is this uncorrelated volatility.
No, right? I understand it doesn't help you, but it helps other players in the energy market, which is going to stabilize prices so that there's less price volatility.
So other players can't do this, right? So you can't, if there's only...
You said at the beginning of the talk that more and more players are doing this, but now we've got people we've got hotels that are scheduling when their washing machines run. We've got people who are scheduling when their cars are going to charge up. You've got refrigerators in the future that are going to cool themselves down extra at night so that they don't have to cool as much in the daytime.
Those are all time-domain shifts. Turning on and off, a completely different thing.
Well, yes, but what he's doing is a completely different thing. But these things will all be evening out prices in other ways. So they're all designed to reduce this price.
We can take this offline because but let me just say. Let me just say that the issue here is exactly that we're shifting stuff around based on price differences, not on local differences, right? A hotel does this based on some threshold that if there's too much demand or if prices rise too high, then it's going to time shift its consumption. Same with cars, right? They're time shifting consumption. This is geo shifting, right? So this is something that nobody can do but but large systems, right? Now, we start affecting prices if there's 10 data centers in one location and there's nothing else there, and they're the ones, suddenly they disappear. That starts affecting the market prices. But if you've got data centers close to other population centers, right, you can either assume the prices won't be affected by your actions, or you can assume that you want to participate with the grid in demand response type things, where they tell you when demand is rising and you can move your stuff away. But yeah.
So do you evaluate at any point how much your savings here are offset by the amount of business you lose because you've increased latency and now people don't buy as much on your page or stuff like that? I mean, one thing that people try to optimize very much is things like load time, right? People have all these studies that say if you increase load time on your page by let's say even hundreds of milliseconds in some cases, you lose some fraction of your business. I mean, if your savings are as small as $3 million, right, then that may get swamped by the fact that now you've moved your CDN or whatnot all the way across the country, let's say. Now your load times go up, and then you lose business as a result.
Right, we'll just get into that. But we haven't moved our CDN across. These percentages are with, well, we'll get to that in a second. Right, yeah.
Quick question. PUE includes what? Why is PUE more than one? The power is going in cooling, that's the primary factor?
Okay. There's also UPS losses and there's power system losses and so on. Right? So, okay, so, all right, so coming back to what this graph was showing was if you vary proportionality, you see a relationship with savings. But the other factor is, are we actually increasing bandwidth costs, right? If you're saving electricity and bandwidth is going up, then there's no point in doing this. This is problematic because we don't have any, I don't have any data on bandwidth costs, and nobody is willing to share it with me.
There's an Atlas report from the Farnham to and so forth. Might look at.
Okay. I mean, yeah, I'm going to get a reference to that from you, but I remember when we were looking at this, we went and we got data on bandwidth costs, and then we took them to Akamai, and the Akamai people were like, this is not what we pay. We pay a lot less. But so apparently, right, so.
That's what it talks about.
Okay. Does it have actual numbers? No. Ideally, what it, yeah. Okay, awesome. All right, so far we've been using a uniform bandwidth model, and a more realistic model if you're renting racks and network ports in co-location centers is a 95/5 billing model, which is that you divide your network usage into 5-minute windows, then you're billed based on your 95th percentile usage of that window. So what we did was we implicitly derived bandwidth constraints from the Akamai workload we had. So we looked at we assumed that they were optimizing their 95/5 bandwidth pricing, right? And then we constrained our routing so that it wasn't violating those. And if we do that, then we get the blue bars, which are a lot less savings. But what you see is you still see the increasing, you still see the increase. The other thing, the reason I was asking for the data is that the value represented by that should be achievable by doing some sort of joint optimization where you're willing to give up some, your bandwidth prices go up a bit, but your electricity prices come down enough for that to be meaningful. So that value should be, if you're Microsoft and you're trying to do this, then you can capture some of that. If you're a graduate student trying to estimate savings, you can't tell how much of that you can get. But this keeps coming up. What about performance, right? It's usually the dominant objective in doing this, in setting routing policy. And these results allow some elevation in RTTs over what Akamai has. But in order to look at the relationship between network latency and savings, let's just focus on this proportionality model. And so the fundamental question is, how far away from clients on average is this cheap power? Are we having to route them very large distances to take advantage of this stuff? The problem is that, again, the workload data we had no network information in it, right? So we couldn't accurately estimate changes in network RTTs. What we could do is we could look at geographic distance, which, if you're assuming that these changes are happening on backbone on well-connected networks, that's a reasonable first approximation for latency. And so we looked at putting a geographic distance constraint on the routing so that we weren't routing clients far away, and then varying that constraint to see how that would affect our savings rates. And so what we get are these two curves. And what's on the y-axis is the client-server distance that came out after we set the constraint. And on the x-axis is the savings, right? And what you see is that as you relax your distance constraints, your savings do go up, which makes sense, right? If you can route further and further away, then you can take more advantage of a lot more markets and a lot more uncorrelated price behavior. The red line is just uniform bandwidth pricing. The blue line is with the Akamai constraints. Now, this region is roughly, say, Boston to New York. So this is relatively close in network time. And what you see is you still get a reasonable amount of savings at this, right? This is closer to the averages we saw in the Akamai data, right? This is Boston to Virginia, right? So this is on the order of 20 milliseconds of network time, right? So with realistic performance constraints, you can still get good savings. Now, if you don't care about performance and network latency if you don't care about network latency, you can obviously get much higher savings.
And these are driven off your perfect proportionality, 10% overhead. You highlighted.
Perfect proportionality, so perfect server proportionality, but not perfect PUE.
Right, but it was only 10%, so this is more of almost a limit than.
Yeah, it is almost a limit, but I've seen data center numbers of 1.13 recently, right, for PUE. So it's not.
Close 1.3 good. Okay. Maybe they're getting there.
Yeah, I mean, these are more experimental data centers, but yeah.
Sorry, you lost me here. So the question you asked was how far were clients from cheap power? So what's the answer?
Not very far. Yeah, not very far.
But how far? What does that mean? Trying to map this graph into the answer to that question. It's sort of answer, and I can't.
Okay, so the answer would be there is some cheap power available nearby, but there's more cheap power available further away, right? So that's. But there's enough cheap power available nearby for this to work. Right, so that's the high level answer. Does that make sense? Okay.
A third of it is available within 300 kilometers.
The what is available?
A third of the net gains are available within 300 kilometers.
So how far are clients from cheap power? That was the question. You're telling me a third of the money by 300 kilometers.
I simplified the question too much, but yeah, they're close enough. But okay, so let me quickly state this before ending this section. Another question that arises is how many points of presence do you need? How many locations do you need your servers at for this stuff to actually make sense? And it turns out that the absolute number doesn't matter so much as the number of electricity markets you're in. So in the US, you can read the paper for a lot more details. There are regional electricity markets, and they're not, some of the boundaries cause price differentials to arise, right? So basically, the more regional markets you're in, and there are about 6 of them in the US, the more savings you can get. So what the y-axis is showing you is if you look at all the possible subsets of locations and you calculate the minimum prices across all of them, that's a best case possible case that's ignoring capacity constraints and so on.
So the units there are dollars per megawatt hour.
Yeah.
No, I understand.
Yeah. But yeah, so the high level point here is you don't need a lot of locations. So you don't need hundreds of locations for this to make sense. You need on the average of 5 locations, and you're going to start seeing significant savings. They have to be well-picked 5 locations, but they have to be 5 locations. Okay, so what does this mean for practical? What are the practical implications for people running these systems, right? And I already said that what we're going for is not, here's how you should build your system. What we're going for more is, so now you've already built your system, how can you reduce the total money you're spending on it, right? So can somebody go and just implement this stuff and start reaping the rewards? It turns out that anybody with multiple locations, some energy proportionality, and metered billing can. But there's almost nobody that fits that right now. So for instance, to use this, people like Akamai would have to go in and renegotiate their power contracts, because when you're buying space in co-location centers and so on, you're billed based on your peak power, right? So you go buy a rack and it's got some power rating, and you pay based on that, right? But if you look at the economics of the issue, what ends up happening is the data center operators are beginning to lose money because of what's happening on the energy market. So it's in their interest to start metering the billing and to start indexing it to these wholesale market prices. So we think that the energy trends are favorable, so that you're going to end up with a lot more people who have access to metered locational hourly billing, and they can start using these techniques. Yeah.
So, like, Google recently acquired a license to play in the energy market, right? So what does it take for, I don't know what their plans are, but I'm wondering, like, in terms of like how the electricity grid itself is structured, like what does it take for, Microsoft or Google to become a player, so that you're not you're not held hostage to whatever the utility company wants to do. With
So
pricing.
I have no idea what Google's plans are. I don't think you have to go that far. I think because there's a lot of talk about the smart grid, right? And one of the aspects of the smart grid is that, if you put solar panels on your roof, right? If you're not using that energy, you can feed it back into the grid, right? And you can make some money off that. Now, I know people who've done that in Massachusetts, who are installing these solar panels, are reselling energy based on the software is reselling energy, right? So
I think the issue is that you can be a silver trader without having a warehouse in which you store your silver, and no one knows yet whether Google plans to be that type of energy trader or someone who's actually going to have facilities and assets and ship power around.
So Microsoft also trades electric vehicles.
We hedge.
Yes.
We participate.
So mostly to guide hedge costs.
Yeah.
So if that's all they're doing, then that's just run of the mill.
Okay, so, all right. So these are the practical implications for if you're trying to reduce, if you're trying to use power demand routing to reduce electricity expenses, right? What I've told you so far is that yes, there's enough price volatility, and you can exploit it, and you can get meaningful. It looks like you can get meaningful savings, but you might need to renegotiate contracts, right? So the next step is to use the same sort of technique and to try to reduce your environmental impact, the system's environmental impact, right? And this is ongoing work, and I guess I only have 10, 15 minutes to cover it, so this is going to go by quickly. The key insight, the key thing to realize here is that the pollution per watt varies in time, right? So if you're drawing watts from the grid, the amount of CO2 per watt for that is a time-varying signal. It's not constant. A lot of people talk about this as average CO2 and stuff, and that, right? I'm sorry?
You have the wrong unit. It's pollution per joule, not per watt. Watt per hour is energy.
No, yeah. Okay.
Anyway.
All right. So the point there is that the reason this varies is because the mixture of fuels that's producing that power, it varies in time. So remember I told you about these auctions happening on the grid? So they're happening once every hour, right? So the grid operator is telling which power plants how much energy they should be producing at any given point in time, right? So at different points in the day, you've got different numbers of gas turbines running, different numbers of nuclear. Well, you've got this base load, which say is nuclear, and then as demand in the grid rises, you allocate more and more gas turbines, and as it falls, you deallocate them, right? So that causes the fuel mix to change. And if you're thinking about renewable power like wind, that by its definition, by its very nature, is intermittent. So that's going to be causing more of this variation to feed into the grid, right? And then there's regional differences, right? So far I've said it's varying in time, but it also varies geographically. So different regions produce energy in different ways, right? So you've got some regions with lots of nuclear plants, and other regions are using coal to do the same sort of work. You've got regions that use hydroelectric power versus regions that very heavily use fossil fuels, and there are regions with more wind power, some with none at all. So you get the same sort of locationally differentiated, time-varying, uncorrelated signals that we got for electricity prices. You get them for these pollution per watt or pollution per joule numbers. And so what we propose to do is you want to use the same power demand routing technique to optimize your system's environmental impact, so the amount of pollution it's generating. And you can just think of this as a different cost function, CO2, for example, instead of dollars. And the specific formulation that we look at is something we call the marginal environmental impact of the system, right? So building your stuff is going to have some environmental impact, and those sort of analyses are important. So these cradle-to-the-grave analyses of, if I build my data center somewhere, how much am I, amortize that cost over the life cycle and so on. But what we're going to be looking at is just the marginal environmental impact, which is, if I increase the power consumption at a location at a given time by delta, how much additional pollution am I generating because of that? And so we're going to look at a linear simplification for that. And what we're going to look at is this notion that you've got this pollution signal, and we're just going to multiply it by the delta power at each location. That gives us the pollution of that location. Now, there's a question about which pollutants you should be paying attention to. Most of the time you hear people talking about carbon, but there are the two other main ones are the nitrates and the sulfates. And you can think about, we've been vague about what this pollution per watt units are. And you can either just stick to grams of CO2 or something if you want something that news organizations can pick up on and understand, or you can be more accurate and use some sort of combination, some abstract unit that captures, the relative environmental impacts of the different pollutants. You can be a lot more complicated about this. It turns out that at different points in time, if you release, say, sulfur dioxide, it's okay because the wind is blowing and the sun is shining. But if you release it at another point in time, it's bad because it's going to do something to the environment. So that's another factor that can play into this that we're not really going to talk about. But okay, so let's focus just on carbon, right? So what if we wanted a carbon cost function that we could use in our routing algorithms, right? So what we want is some grams of CO2 per watt that we can then plug into this power demand routing. Now, it turns out that what's happening is that sensors are being placed at power plants that are measuring activation and fuel mixes and so on. And in places, you can actually get XML data feeds where the grid operator aggregates everything and hands it to you. So, for instance, in this point, it's saying, look, the fuel gas turbine, it's contributing 40.7%. And the coal is contributing 35%. And you can just get this, and then you can sum things up, and you've got your nice signal, right? And if you go to this website, you can actually look at the UK's, the varying signal in the UK, right? So this stuff is not stuff that's 5 years down the line or something. It's actually being implemented in a lot of places. Now, like prices, we can just integrate these systems, these signals into our routing algorithms, and then we can, make things greener. But there are some complications. There's not enough data for, this stuff is not available everywhere. And even in the places where it's available in things like, here's how much the average CO2 varies on the UK grid, not here's how much London varies, right? So there's not enough spatial resolution. And there's not enough historical data for me to be able to go and rerun that analysis and say, this is how much percentage reduction you could get in your pollutant levels or something, right? But what can we do today? Can we have some useful functions that we can use in routing? And one of the ones that people talk about is, let's just route things to places where the intermittent energy, these renewable energies are producing, at any given point in time, they're producing a lot. So you can write down this as, just the fraction of the green energy, that gives you a time-varying function. And the thing at the end is the local average CO2 of the grid. So if you're in Texas, that's going to be different. If you're in California, that's going to be different. And just at that point, you've got one function you can start routing around based on. But you can be more accurate, right? You can look at other signals that you can get from grid operators. One of the other signals you can get is the level of demand on the grid, right? So you know during the day how much demand is being placed on it, and then you can use that in addition to a regional model to try to map that into the level of pollutants on the grid. So let's look at it this way. You've got 3 regions. One of them is using coal for their base load and then gas. Another one is using nuclear for their base load, then gas turbines. Another one is using nuclear and hydro. And they've got different relationships between load and the amount of pollutants. So, right, so if you're coal and you're adding gas turbines as you go along, the higher the load is, the cleaner the energy is, because gas is cleaner than coal. With nuclear, it's the opposite relationship, right? You start out with something that's relatively clean on a CO2 level, and then you start adding more and more marginal pollutants to it. So it gets dirtier as the load increases. And with this nuclear and hydro, it's a different relationship, right? So using these, you can just come up with some synthetic numbers, and you've got your cost functions that map your load to some pollution signal that you can then use routing based on. Now, don't pay too much attention to those numbers. But the point is that you can come up with some synthetic cost function that is time varying that you can do today, and you can use it to optimize the environmental impact of your system. So in conclusion, what I've talked about in this talk is this perspective of power demand routing, right? Just using your routing policy to start shifting power around. And doing that not from an energy efficiency perspective, but doing that to try to minimize some sort of cost function. So the first cost function that we talked about was just electricity expenses. And what we found that we could do was we could exploit the price volatility in markets, and we could save a lot. Now, in retrospect, these dollar numbers shouldn't have been here because nobody seems to like them in this audience. Right. But the other thing you can do is, and this is a lot harder to quantify just because of the lack of data, some gold standard data that we can measure our impact against, is you can use power demand routing and pollution. You can exploit the pollution volatility on the grid to route around regions that are getting dirtier as the day goes on. So there are a number of extensions with this work, right? And this comes a little bit into the future work that I would like to do. One of them is this idea that this keeps coming up, right? Where so far we've been assuming that you're just passive participant in these markets. You're sitting on the sidelines. You're just looking at the prices and reacting to them. It's a lot more interesting when you start talking about interactive participation, right? So if you start talking about actively participating in these demand auctions on the grid, where you can bid the value, you can say that I'm willing to reduce my load in this region, but this is how much you have to pay me to do it. And this stuff is possible today, but how to construct those bids, because you need to have a model of how much your client demand is going to be at that data center, and how to bid optimally and so on across lots of data centers. That's a complicated problem. Or you can do something simpler, which is just demand response. But then you need to understand the demand response is the grid tells you when to back off, and you back off. And if you don't back off, they penalize you economically for not backing off, right? Now, that's a simpler in terms of you don't have to think about auction theory or whatnot, but you have to think about how that impacts your reliability or your performance, right? If you have to look at how often these demand response events occur, and how best, whether it makes sense to participate in those as a large systems operator. The other extension that I alluded to was you're skewing load based on greenness or prices, but you can also skew load based on energy efficiency. And if you did the energy efficiency-based skewing, what you would see is you would be able to reduce the overall power consumption of your system in addition to saving costs and so on. So that is sort of the extensions that I see for this work. But there's also a lot of related work that I'm interested in. So for instance, I alluded during this talk to this notion of the smart grid, and lots of people talk about the smart grid, and the basic idea is let's have sensors in people's homes, let's have data coming from the grid, and let's figure out how to do something with that. But a lot of the work you see on it, it's not that interesting as far as I can tell. What I'm really interested in is this notion that a lot of the stuff that's happening on the grid, a lot of the stuff that complicates issues on the grid is the fact that you have to provision for peak, right? So on the grid, you have to build all these power plants because maybe one day out of the year you consistently hit that load level, right? Or not one day, but a little more. But a way to, just in terms of capacity planning, that makes sense. But what ends up happening is that when you get into those regions, you're having to activate these resources that aren't highly reliable. They're not always activated. Maybe they're really dirty. So it is in our interest to not having to activate them. And one way to do that is just to figure out a way for consumers to back off on their demand or flatten out consumption on the grid, right? And this issue with people talking about electric cars and then having software running in them to charge at night, that addresses part of this concern, right? Where you buy it when not a lot of people are using electricity on average, so you're trying to flatten out your demand curve. But you can, once you start thinking about, people have intelligence embedded in their homes, how you can write software that integrates data from the grid and tries to do automatic responses, right? Maybe dims the lights or something if that's the policy you've set up. And that's good from a public good perspective because it increases the efficiency of the grid. It might be good from an economic perspective because suddenly my electric bills are a little lower. And the idea there is to build more flexibility using using software, and then try to optimize the overall system doing that. But the research problems that I work on, I mean, if any of you read my research statement, I think the third word in it is eclectic. So let me just, oops, okay. That slide shouldn't be there. But anyway, so let me talk about the other big project that I work on at MIT. So years ago, I wrote a master's thesis, right? And the master's thesis was on this issue about opportunistic wireless network aggregation, right? So the idea was that we have a node, and it's got lots of wireless radios on it when we drive it around in a vehicle or whatnot, and what it does is it continuously scans and aggregates whatever wireless bandwidth is available to it. And so, and then the idea there was, let's have a lot of bandwidth, and then we can use that bandwidth to try to send high-fidelity video. And so the application we were going for was this mobile telemedicine application. And the idea was that you've got an ambulance or you've got a community hospital, they don't have experts. They don't have specialists in a certain field. They don't have cardiac specialists, they don't have neonatal specialists. Because what's been happening in medicine is that you've seen this concentration of expertise. You get these big medical centers that have lots of experts, and then you have patients who are just spread out because that they live where they want to live. And so whenever something bad happens, if they're lucky enough, they'll make it to a specialist. If not, they'll end up at a community hospital, and then they'll get stabilized and then shipped over, right? So we're trying to address that by, historically, telemedicine has been used to address that, right? If you think you're having a heart attack, you sit down at a terminal and a cardiac specialist views you over a video link, they can walk you through certain tests that they can then tell whoever's with you to give you certain medicines which might kill you if you didn't have the right disease, right? So the problem with that has been that you need to have a lot of fixed investment in setting up these satellite telemedicine centers. So what we're doing is, let's use this wireless networking technology, and let's just reduce the barriers to entry to it, so that somebody just walks out with a briefcase, and suddenly you've got this high definition video link that they can establish and then talk to doctors. And so I wrote most of the code for that, then mentored a couple of grad students that have developed an application for neonatal patient care. And so what we're doing right now is we're doing a clinical deployment at Children's Hospital Boston. And the idea there is what they do is, when people deliver babies, very sick babies, maybe the size of my hand, at community hospitals, those babies are stabilized and then shipped to these experts who then make sure that they live. And what we're doing is we're deploying this system at the community hospitals and at the specialist center, and then actually seeing if it improves clinical outcomes, right? So we've already proven that it works technologically. We've driven this around in cars, we published papers on it, and we know the video part works. But does this actually affect the medical part? And so that's what we're going to be finding out in the next 6 months or so. And we're also transferring the code to Quanta, the people who make MacBooks and so on, because they seem to want to turn this into a product. But I bring this up as a way to show that I work on lots of different problems, but also this is also something that I'm interested in, just the medical application aspect of software. And moving beyond this, what's very important is that if you look at the resources, the resource constraints in hospitals, one of the most constrained resources is the attention of doctors, right? The attention of experts. And what you can do with software is you can figure out how to triage patients so that the alerts that reach doctors are relevant and are for things that they should be responding to. So prioritize them and triage them, right? What happens right now is you've got systems that generate alerts with too many false positives. And when doctors see all those alerts, they just tune them out, right? Then they'll say, oh, I'm not going to pay attention to this alerting mechanism, this nurse, this EMT, whatever, or this piece of software. What I'm going to do is I'm going to have to go there and start from scratch. And I believe that software can play an important role in, especially since we're getting so good at collecting lots of data, collect that data, mine it in real time, and try to figure out how to best notify doctors. All right, I think that's time, so I'm going to end here.
We have time for one more question.
question is about sort of most of your talk about the work we've done on energy. So I found like you asked very interesting questions. Actually, the sort of questions you raised, I thought they were fantastic. And along the way, you had to make some assumptions trying to answer those questions. And I can relate very much to that. In that a lot of these numbers, you don't have in academia, and they're hard to get. But there's a whole bunch of assumptions you make, about numbers, about sort of energy contracts, about bandwidth costs, about placements, data, and so forth. My question to you is, which out of all these assumptions, so you feel like if you were to know the answer, if you have actually access to the data, would really, get you a long way towards sort of answering these questions more definitively?
I think the way I think about this, the problem is as it's an optimization problem, right? It's a multi-objective optimization problem. And so what you're trying to optimize is your bandwidth cost, your latency, or your performance penalties. You're trying to minimize your performance penalties, and you're trying to minimize the service cost, like these electricity prices or whatnot, right? And if I had all those numbers, or if you're just trying to pose this as a formal problem rather than as a how something I can build and run my analysis over, right? Then I think bandwidth, understanding how that varies locationally is most important for me. Maybe it's just because I'm looking at CDNs and so on, and so they tend to be.
Just trying to understanding how bandwidth varies.
How bandwidth, the locational patterns in its variation, right? Because I understand how prices vary by location, because there's a large body of theoretical work based on that. There's a large body of a lot of economists have looked at that and so on, and there's a lot of data there. There's not a lot of published work that I know of on bandwidth. Maybe a lot of the pricing is ad hoc. Maybe that's why it's like that. So understanding that would be useful, but better understanding the sort of contracts data center operators are actually engaging in to buy and sell electricity. That's also useful. I don't think that's going to be as useful because I'm already arguing for a contract renegotiation. So, yeah.
Right. I think we lost all our crowd.